Introduction of this part of this chapter. So just I'll read out. The ray optics uses the geometry of straight lines to account for the macroscopic phenomena like rectilinear propagation of light, reflection of light, and refraction of light, etc. However, the microscopic phenomena like interference, diffraction, and polarization could not be accounted for by ray optics. Okay, so as you know that some of the macroscopic phenomena like the rectilinear propagation of light, reflection and refraction can be explained by making use of the ray optics. Okay, like some of the microscopic phenomena like it can be interference, diffraction, polarization. So this type of phenomenon cannot be explained in ray optics. Okay, so the next is to explain this phenomena, concept of waves was introduced. The new branch of physics based on the wave concept of light was called wave optics or physical optics. So as you know that in this chapter we are going to consider the wave nature of light. Okay, so hence the branch of physics based on the wave concept of light is called as wave optics or physical optics we call. Okay, so the next, the wave theory of light was put forward first of all by Huygens and later on modified by Fresnel. According to wave theory of light, light is a form of energy which travels through a medium in the form of transverse wave motion. The speed of light in a medium depends upon the nature of medium. So as you know that this wave theory of light concept was first put forward by the scientist Huygens. Okay. Later it was modified by Fresnel. Okay, and according to this wave theory of light, light is a form of energy which travels through a medium in the form of transverse wave. I think you are aware of this transverse waves and longitudinal waves, right? So in the last year itself, in the chapter of waves, you have studied these things. What is transverse wave? What is longitudinal waves, right? So hence, in this wave theory of light, light is a form of energy which travels through a medium in the form of transverse wave motion. Okay, so the next is the speed of light in a medium depends upon the nature of the medium. Okay, the speed of light, as usually you know that it depends upon the nature of the medium. Okay, so this is regarding the introduction of this wave optics. Okay, so first of all, as you know that in the case of ray optics, we just gone through about this the reflection of light, refraction of light, and the rectilinear propagation of light. So these are some of the macroscopic. Coming to the microscopic, like interference, diffraction, polarization cannot be explained by ray optics. Okay, in order to explain this phenomenons, we make use of the concept of waves. Okay, so hence the branch of physics which is based upon this wave nature of light is called as wave optics or physical optics. Okay, so it was first put forward by, this concept was first put forward by Huygens and later it was modified by Fresnel. Okay, and in this uh, wave theory of light, light travels in the form of transverse wave. Okay, so this is regarding the concept, that is the introduction. Okay, so next coming to wavefront. Okay, so see here, what is wavefront? It is said that a wavefront is defined as the continuous locus of all the particles of a medium which are vibrating in the same phase. Okay, I think you are aware of this phase, in phase, out of phase, right? Okay, this thing about the phase you have been studied in the oscillation chapter last year, right? So you can see here you have, let us say that this is a wave. Okay, so let us say that the particle this is one particle and this is the second particle. Okay, when you compare both the particles, both are in phase. Okay, so we call this type of particles as the particles are in phase. Let us take another example, that is, let us say that particle 1 is at this point. Okay, next particle 2 is at this point. Okay, so now these two particles are called as out of phase, we say. Okay, we say that these two particles are out of phase. Okay, I think now you have been got an idea what is when do you call the particles are in phase and when do you call the particles are out of phase, right? So hence the wavefront is defined as continuous locus of all the particles of a medium which are vibrating in the same phase. Okay, so as you know that when you take a point source, okay, when you take a point source, let us say that this is a point source, you can see in the figure 1 there. Okay, the best example is nothing but see, just assume that you have a river or a pond. Okay, so assume that you have thrown the stone, okay, into the pond. So as you can see, the disturbance is produced, right? So that disturbance will be moving away, right? So when you throw the stone from that point, the disturbance moves outward, right? So that disturbance itself, we call that one as the waves, right? Waves are created and it moves outward, correct? So that point, okay, that locus of all the particles of a medium which are in same phase is called as wavefront, we call. Okay, so in the first figure you can see about that wavefront. Okay, so here let me make it little more easier. Okay, let us say that this is a pond. Okay, you have thrown a stone at this point. Okay, so now as you know that the disturbance has been created, that is the waves are created. Okay, it moves in the outward direction, right? So when you take the particles which are at this point, this point, this point and this point. Okay, so when you take the particles and when you draw a envelope, okay, when you join all those particles which are in the same phase is called as the wavefront, we call. Okay, so wavefront is nothing but it is defined as the continuous locus of all the particles of a medium which are vibrating in same phase. Okay, so this is regarding the wavefront. Okay, so do one thing, just go through about that wavefront first. Let me know whether you have understood that wavefront, because after that we have spherical, cylindrical, plane wavefront. Okay, first of all you should know what is wavefront, then it will be easy for you to understand the spherical, cylindrical and plane. Okay, so just go through that wavefront. Yes, have you understood this wavefront? Yes, reply. Why is that you people don't reply itself? At least say whether you have understood or not. Then what is the use? Okay. So see here, the next is nothing but spherical wavefront. Okay. Let us see what is that spherical wavefront. Okay. When the source of light is a point source, the wavefront is a sphere with center at the source. Okay. So see here, what is spherical wavefront? Spherical wavefront is nothing but when the source of light is a point source. Okay. Let us say that, which I have explained right now, the same thing. Okay. Let us say that this is a point source. Okay. It is little bit difficult to draw on the screen. Okay. Okay. See here. So let us consider this as the point source. Okay. So the wavefront is a sphere with the center at the source. So as you know that the waves, okay, the disturbance moves in this form, right? In all the direction, the light propagates in all the direction, correct? So what happens here is, so you need to draw the particles. You need to draw a envelope so that the particles which are at the same phase. Okay. So hence this will be a wavefront. Okay. So this is a sphere, right? So hence this is a spherical wavefront we call. Source as the center. Okay. So the simple thing is here, whenever you have a point source, okay, the light is propagated in all the directions, right? Correct. So if you consider this as a point source, let us say that the light propagates in all the direction. Okay. So let us take the points where the particles are in the same phase. Okay. So these are the point where all the particles are in the same phase. Okay. And this wavefront is nothing but spherical, right? And this wavefront is called as spherical wavefront with the source at the center. Okay. This is regarding the spherical wavefront we call. Okay. So next, cylindrical wavefront. Let us see that a line source of light, example, an illuminated narrow slit, produces a cylindrical wavefront in an isotropic medium. A cylindrical wavefront propagates in the form of coaxial cylindrical surface. Okay, you are aware of this isotropic medium, right? In the ray optics itself, we have gone through. So now, what do you mean by this cylindrical wavefront? Okay, when is this cylindrical wavefront is produced? Okay, suppose the source of light is a line source. Okay, if you ask what do you mean by this line source, it is nothing but you can take a narrow slit. Okay, so you are aware of this slits, right? Okay, this is called as the slit with a small gap. Okay, this is called as a slit. Okay, when the source what you have taken is a line source. Okay, so the wavefront produced will be a cylindrical wavefront. So in the figure B you can see there. Okay, suppose let us say that we will take a line source. Okay, so we will take this point here. Okay, as you know that all the particles light travels in all the direction, right? Light travels in all the direction. Again the same thing, let us say that the particles which are in same phase. Okay, so that thing I'll indicate by arrow mark. Okay, so we will take the particles which are in same phase and we will draw a and we will join that. Next, similarly, we will take this point. So we will take all the particles which are in same phase and we will join this. Okay, and if you join this, so this is nothing but a cylindrical wavefront we call. Okay, whenever you have a source of light as the line source, okay, the cylindrical wavefront is formed. Okay, so this is regarding the cylindrical wavefront. So we have just taken a 2 points here, point A and point B. Okay, to explain this we have taken a point, this as A and this as B, and we have explained this. Okay, so this is regarding the cylindrical wavefront. Okay, so next it is regarding plane wavefront. Okay, so in an isotropic medium, a small part of the wave surface of a spherical or cylindrical wavefront, when viewed from a very large distance, appears to be plane and is called a plane wavefront. Okay, so as you know that you have a, let us take an isotropic medium. Okay, so a small part of the wave surface of a spherical or cylindrical. Okay, so this is spherical example for an spherical wavefront and this is an example for cylindrical wavefront, right? So when you take a small part of the cylindrical wavefront or spherical wavefront, when this wavefront has is being viewed from a very large distance, so what happens, it appears to be like a plane. Okay, so this itself is called as the plane wavefront. You can see here, let us say that the source is situated at, the source is placed at infinite distance from us. Okay, when you view that wavefront, okay, a small part of a cylindrical or spherical wavefront, when it is viewed through a very large distance, so it appears to be a plane wavefront like this. Okay, so this is regarding the spherical wavefront, cylindrical wavefront and plane wavefront. Okay, so please go through about this three, it is very important. Okay, again go through what do you mean by wavefront, then spherical, then cylindrical, then plane. Okay, because until you don't understand this wavefront, the rest of the concept which we go through in the upcoming topics, okay, so it will be not able to understand. Okay, make sure that you have understood about this wavefronts. Go through once, go through for a few minutes. Okay, others explain wavefront definition once again, sir. Okay, see here, others. The wavefront is nothing but it is defined as a continuous locus of all the particles of a medium which are vibrating in the same phase. Okay, so as you know that, let us the best example is nothing but a stone thrown in a river or a pond. As you know that the waves are created, right? How the waves travels in the form of crest and trough, right? Correct. So what do you mean by this crest and trough? First of all, this is crest and this is trough, right? So let us say that the waves moves like this. Okay, take this point, again this point. The particles which are at crest. Okay, the easiest way I'm saying to understand. Okay, so when you join this, all the particles which are at the crest, that itself is called as the wavefront. Okay, so or else you can understand like this also. The same way, let us say that this is a pond. So this is a pond. So let us say that you have been thrown a stone at this point at the center. So what happens? The waves are the disturbance is created and it moves outward, right? It keeps on moves outwards and disappears. I mean dies we say. Okay, the wave dies we say. Correct? Okay. So let us say that the waves, that is the disturbance, passes in the form of crest and trough. Okay, you can see here like this in all the direction, right? Okay, so just join all the points which are at crest. I mean the particles which are in vibrating in the same phase. So these are the particles which are vibrating in the same phase, and the locus joining all these particles which are moving, I mean which are in the same phase itself, is called as wavefront. Okay, is it fine? Is it fine, others? Okay, fine. I hope you have understood, right? Yes, have you understood the spherical, cylindrical, and plane wavefront? Okay, fine. So next is nothing but CM. In a given medium, we can draw a set of straight lines which are perpendicular to the wavefront. Remember, rays are always normal to the wavefront. According to Huygens, light energy flows along rays. Okay. So see here, what you need to observe here is you need to keep in mind is nothing but the rays are always normal to the wavefront. Okay, so the best example is nothing but here, this is the figure A, when you go through the figure A, this is a plane wavefront. Okay, so these are the light rays. Okay, so these are the wavefront. Similarly, see here, when you go through the figure B here, this is the source, and you can see this is nothing but the light rays. Okay, and this is nothing but the spherical wavefront. Okay, and it is diverging, right? So you can see, as you go the wavefront, as it is going away from the source, it is diverging. Okay, so hence you can see in this case also, the light rays and the wavefront are perpendicular to each other. Okay, normal or perpendicular. And again in the figure C, you can see here, it is nothing but converging wavefront. Okay, the light rays are coming in different directions and they are meeting at a point. Okay, and you can see this is the wavefront, converging spherical wavefront. Okay, so even in this case you can see there, the light rays and the wavefront are perpendicular to each other. Okay, this is very very important. So keep in mind that always the light rays are perpendicular to the wavefront. Both are perpendicular. Light rays are perpendicular to wavefront. Okay, so this thing you should keep in mind. Okay, I hope that you have just gone through, I mean you have understood the things what we discussed in today's class. Okay, so I'll do one thing, I'll just conclude my class uh, till here. Okay, so just go through, I'll just forward these notes in the group. Just go through introduction, wavefront. Okay, once again go through the wavefront and different types of wavefront. Okay, so you need to remember these things. Okay, how, what is spherical wavefront, what is cylindrical wavefront, and what is plane wavefront, and how, I mean the rays are always normal to the wavefront. These things you need to keep in mind. Okay, even in the upcoming topics we keep on study the different topics based upon these things itself. Okay, so with this thing I'll conclude today's class. Okay students.